Usually when you watch like a 100-meter sprint, it's incredibly obvious who is moving fast. You just watch the runners tear down the track.
Yeah, exactly. It's entirely visual, right? You see the speed and, well, you know the result straight away.
But then you step into your chemistry lab and you're asked to measure a reaction rate. Suddenly you're just staring at a clear beaker, just waiting for something to happen.
Right, which can be pretty frustrating.
Yeah. So, okay, let's unpack this. Today's deep dive is your shortcut to mastering your chemistry assignment. We've actually taken your lab instructions, your class notes, and the marking rubric and, well, distilled them down so you can absolutely nail this practical.
And I reckon it really starts with understanding what reaction rate actually is.
Yeah.
At its core, it's just how quickly your starting material, so your reactants, turn into your final products.
Okay, so there are the runners in this scenario.
Spot on. But these runners are microscopic particles and they're constantly colliding with each other.
Right, but since we can't exactly, stick a tiny speed camera on atoms, I imagine we have to play detective a bit in the lab.
We do, yeah. We have to look for the clues those invisible collisions leave behind. We have to rely on visible, measurable changes.
Okay, so what exactly are we looking for then?
Well, there are four major indicators you can track. First is gas production. You can capture the gas being created and literally just measure its volume over time.
Oh, or alternatively, you could measure mass loss, right?
Yes, exactly.
Which, it makes perfect sense when you think about it. Like, if your reaction creates a gas and the flask is just sitting open, those gas particles literally float away.
They do. The matter leaves the beaker.
Right. So if you have the whole setup sitting on a scale, you can just watch the weight drop.
Yeah, you're literally watching the mass vanish into the air. It's great. The third indicator is temperature shifts. So tracking the heat that's absorbed or released as bonds break and form.
Makes sense.
And finally, the fourth one, you can track concentration or color changes.
Ah, and that brings us straight to the sodium thiosulfate practical in the assignment.
Yes, the classic one.
For those looking at their notes right now, this is that experiment where you mix the clear liquids, you put the beaker over a piece of paper with an X drawn on it, and, well, you time how long it takes for the liquid to get so cloudy that the X just completely disappears.
Right, and even without fizzing bubbles or some dramatic temperature spike, that color change gives you concrete data.
Because the faster that X vanishes, the higher your reaction rate.
Exactly. And you could even use software like Tracker or Excel to analyze exactly how quickly that opacity shifts.
Okay, but watching a liquid turn cloudy is only half the battle, right? Like you're just saying in your write-up, oh, it got cloudy kind of fast. That isn't going to meet your success criteria.
No, definitely not. To prove the rate, you have to turn those visual clues into hard mathematics. You need to plot them on a graph.
So time always goes on the x-axis, right? And your measured change like color intensity or mass goes on the y-axis.
Spot on. If you're tracking a product being created, your line goes up. If you're tracking a reactant being used up, well, the line goes down.
Okay, but wait. Here's a massive trap I know a lot of students fall into when they're comparing these graphs.
Oh, the height trap.
Yeah, exactly. Let's say my line ends up way higher on the chart than a classmate's line. It's super tempting to assume a taller graph automatically means my reaction was faster, right?
Oh, absolutely. Confusing the total amount of change with the rate of change is probably the most common mistake you'll see in these write-ups.
So a higher line doesn't mean faster.
Not necessarily, no.
Sure.
A graph might end up higher overall just because it produced more gas in total.
Mm-hmm.
But if it took, say, 20 minutes to get to that height instead of 20 seconds, the rate was actually much slower.
Ah, got it.
Yeah, rate is strictly about the gradient, the slope. It's about how quickly the change happens, not just how much change happened in total.
Okay, so your grade really hinges on reading the story that slope is telling you. A steep gradient means a fast reaction. A flatter section means it's sluggish.
Yes, and you have to remember the underlying chemistry here to explain why in your assignment. Never assume a reaction just chugs along at a constant speed from start to finish.
Right, because they almost always kick off with a really steep slope. You've got an abundance of reactant particles just bumping into each other left and right.
Exactly. But as those reactants get used up, there are fewer and fewer particles left in the beaker to collide.
And fewer collisions mean the reaction has to slow down.
Spot on. The gradient of your graph gets flatter and flatter until eventually the line completely levels off into a horizontal plateau.
Which is your visual proof that the reaction has essentially finished.
Yep, it's done.
Okay, so to wrap this up, instead of treating your rubric like a simple checklist, you really need to let the graph guide your explanation. To smash this assignment, your write-up needs to clearly link the shape of that curve to the reaction speed.
Right. Use your data. Compare the steep slopes of your fast trials against the flatter slopes of your slow trials, and make sure you're using accurate chemical terminology.
Absolutely. So before you wrap up the task, make sure you've gathered your clear observations, plotted those measurements accurately against time, and double-checked that you are actually analyzing the gradient, not just the final amount of product.
That's the key right there.
Yep. And as you're staring at your final graph, right as it hits that flat plateau, I want you to ask yourself, what exactly is happening to those microscopic particles at that exact moment to make the whole reaction just stop?